Okay, so if we divide the observed wavelength by the emitted wavelength in this table, the wavelength observed divided by the wavelength emitted is always 1.058. You can check that with the calculator. And that's 1 plus V over C. So we subtract 1 from both sides and we get 0.058 C for the velocity. So again, because we know what the emitted wavelength is, we can actually know what the velocity is. So again, the Doppler shift actually has been known to cause problems, for example, in Kmart, for instance. You might have heard of the blue light special in Kmart, right? Well, some people are so attracted to blue light specials, they fly towards them at relative speeds inside the Kmart. Technically, no speed limit in the Kmart, it's actually legal. But when they fly toward the red light special, blue light special, they don't see it as a blue light special anymore. They see it as an ultraviolet special. And they get very upset. There's a lot of lawsuits about this. As long as I your career and the legalities of Doppler shift, I'm going to get into that. So, this very same process of the Doppler shift of radiation has actually given us the best evidence we have for the existence of black holes. You know, there's always this riddle about black holes. Well, if they're black, you know, they absorb light, and how could you ever see them? You know, people naturally ask this question. It's a very reasonable question to ask. Black hole, you don't see it. How could you discover something you can't see? And the answer is that we actually can't discover the black hole itself, but because of their strong gravity, they have such a strong pull on the matter around them that they can create very high-speed motions, very high-speed orbitals. Like, for example, you know, the moon orbiting around the Earth has a certain orbital velocity, probably 2,000 kilometers per second or so. But if the moon could replace the Earth with a black hole and left the moon where it is, well, now the moon would be whipping along at, you know, probably maybe a quarter of the speed of light or something. So as you increase the mass of the thing that stuff is orbiting around, you naturally increase that velocity, the orbital velocity. So basically, when we look at certain sources in our galaxy and other galaxies, and we send the light through a spectrograph, what we sometimes see is a set of peaks that are offset. And what we understand this to be now is actually emission from ionized hydrogen gas, so hydrogen gas at high temperatures. And what we're seeing is the edge of a disk of matter that's orbiting at very, very high speed. One edge of the disk is orbiting towards us, the other edge of the disk is orbiting away from us, and because the speeds are so high, we're getting the blue shift from the hot gas that's moving towards us on one side, and a red shift on the other side. But it's all mixed together because we can't actually, well, in some cases we can sort of see a little bit of the disk, like this situation here. What we see when we look at the two different sides is, again, you know, a red shifted peak and a blue shifted peak. But the amount of the shift between those two peaks is a way of measuring the velocity using the same formula that we just talked about. And what we find is that the shift between those peaks on the blue shift side versus the red shift side is so high that the orbiting gas is orbiting with like at least half the speed of light, or maybe even a little faster than that. And there's no other object that we can conceive of other than a black hole that creates that kind of orbital velocity. So we end up with very strong, albeit circumstantial evidence for black holes that way, because we see direct evidence of super high speed motion. Now this is my son. That's my son. And his cat. And the reason this is a random family photo, but this cat is one of the unusual things about this cat. There's actually a whole bunch of them. But she just loves cats, as you can tell from her expression. Just has the same for hats. There. Should try to check that black hole. Put that in kind of random spot. But anyway, she likes the fire hat especially. All right, so well, we've talked about atomic spectra a little bit. The higher atomic numbers have more protons in the nucleus, of course, right? If we work our way up to iron, for instance, it has 26 protons in the nucleus. Now, remember that I said that it's the number of protons in the nucleus that dictates, it determines what the actual energy values and all their differences are between the levels. So it's the structure of the nucleus that's going to determine the spectrum that you're going to see. Now, when we get to the complex atoms, like iron in particular, there's many, many, many rather closely spaced transitions possible because of the complexity of the proton and what that does with the electron energy levels. And when we talked about, if you remember, we talked about the Fraunhofer absorption spectrum, which is the continuous spectrum of the sun with all those black lines all over it, right? The continuous spectrum of the sun isn't really a pure continuous spectrum. It's a rainbow, but with hundreds of little black lines on it. Well, those black lines mostly actually represent absorption due to iron in the atmosphere of the sun. So, for example, if we suppose that the green here is the radiating surface of the sun, there's some gas above what we call the photosphere, which is like the yellow surface of the sun. There's some gas above the yellow surface of the sun, which is a little bit cooler. And iron is very hard to ionize completely, so there's still some intact iron running around there. So we have this mist of gas above the solar surface, which includes iron. And that iron, because it's still atomic, is going to cause these absorption lines. It's just exactly what we were talking about before. The yellow surface of the sun is like that incandescent bulb, the white light source. Then you have this cool gas. It's actually pretty hot, but relative to the surface, it's cool. It contains some iron atoms. And so the light coming up causes excitation of the iron, and the iron radiates, but again, it radiates in random directions, so you see that dearth of there's a certain wavelength. So that's actually what's producing, that's what's going to produce the Fraunhofer series of dark lines. Okay, well this is just a little more detail, I'm just going to flash this by you. But you might have noticed that when we look at these different atomic spectra, we sometimes see like groups of lines together, and then we see other groups of lines together that are kind of close to each other. Those groups of lines that we see pretty close together in the spectrum, the reason they're grouped together is because they represent sometimes there's something similar about those transitions. The dominant series is actually the Lyman alpha series, and that's going to represent transitions that involve the ground state. So it's actually the ground state to the first excited state that gives us that red line we talked about. But we also have transitions that involve dropping down to the first excited state. That's going to give us, it turns out, a weaker line, but it's kind of a group of lines that are offset from the group that's around the red line. So we get basically kind of bundles of lines in the spectrum that are grouped together according to where their sort of destination state, whether it's the ground state or the first excited state. Now we can also, in environments that have lower temperatures than stars, we can start talking about molecules. There's absolutely no molecules in the solar atmosphere. So when I spoke a moment ago about how you have the yellow disk of the sun and you have this sort of atmosphere above it with some iron atoms. Okay, yeah, you have iron atoms, but you don't have any molecules at all. Because molecules are very fragile. Molecules, of course, are groups of atoms, but they're very fragile. It doesn't take much energy to cause a molecule to fall apart. One or two, relatively low energy ultraviolet photons, and the molecule's gone. So they're pretty fragile. But in situations that are lower temperature than stellar atmospheres, like you get out farther away from the sun, you can actually get molecular clouds and things like that. Not really so much in our solar system, but even outside our solar system. We see huge clouds of cool gas that we think actually are composed of molecules. So you can have clouds of molecular gas up there. And then you can ask the question, how do molecules interact with radiation? You talked about how atoms interact with radiation. Well, molecules interact with radiation too, and they also create emission and absorption lines, almost exactly the same as atoms. The only real difference is that molecules are a little more complicated because of the fact that they're actually groups of atoms. Okay, so they end up with a couple of extra ways of storing energy. Now, in the case of atoms, we only have what we call electronic storage of energy, which is just when we cause electrons to bump up to higher excited states, just like we already talked about. That's electronic energy storage. Molecules can do that too. Molecules can store energy electronically because they do have excited states associated with their electrons. But molecules can do two things that atoms can't do. They can rotate and they can actually vibrate. Okay? Atoms are perfectly spherical essentially, so there's no way to cause an atom to pulsate or vibrate. But molecules can actually vibrate. If you think about H2O, You have two hydrogens and one oxygen making kind of an angled configuration. And there's ways that you can get those atoms to actually vibrate a little relative to each other like a spring. That's a way of storing energy in a molecule that's not available in an atom. Likewise, because molecules are not symmetrical, like atoms are, molecules can rotate. It's not really meaningful to have a rotating atom because the electrons are already rotating anyway. You can't spin an atom. It's just an electron cloud around the nucleus in the first place. There's no way to really spin that. But if you think of H2O, again, it's got distinct two hydrogens and oxygen. You can spin that thing. It's an object that you can spin. Anyway, so the bottom line is that each means of storing energy leads to different energy levels. And it's the spacing between those levels that then tell you what kind of radiation is involved in the interaction we're talking about. When we talk about electronic transitions in a molecule, then we're talking about visible and ultraviolet lines, just like when we're talking about atoms. But when we talk about vibrational transitions, it turns out that the vibrational energy levels are much closer to each other. So the differences in energy between two vibrational levels are pretty small amounts of energy. So you're talking about longer wavelength radiation. So the vibrational transitions produce infrared lines. Remember, infrared is longer wavelength, lower frequency, lower energy than visible light. And that, again, is happening because the vibrational levels are actually pretty close to each other. So it really doesn't take that much energy to shift between them. Now, when you talk about rotational transitions, it turns out those transitions are even more closely spaced with energy. So when you have rotational transitions of a molecule, then you're talking about emitting or absorbing radio photons, really low energy photons. But with knowledge of this, you can detect things like clouds of hydrogen gas in space. Clouds of hydrogen gas in space produce a characteristic radio line that we can actually detect. All right, so this is just a panel from the book that goes through what I just said. We have the electronic type transitions on the top. This is carbon monoxide. So we have electronic transitions on the top that are going to tend to emit and absorb visible light. We have vibrational transitions here, which in fact in solar vibration would result in infrared radiation, and rotational modes are going to result in radio radiation. And by the way, these the amount of energy that we can put into the rotation is quantized. It's not like a macroscopic object like a spinning top or something. A spinning top you can spin as fast as you want. Put as much kinetic energy into a spinning top as you want. But these are basically microscopic particles we're talking about. So they're actually subject to quantum rules. So the amount of energy that we can put into the rotation is actually quantized. And actually gives you the discrete levels that we're talking about. So just to see how much of a difference this makes in terms of complexity, we have here the spectrum of atomic hydrogen on the bottom. There's our characteristic strong red line, or 6,000 angstroms, 750 nanometers. And there's part of that series I was talking about. But look at the spectrum of molecular hydrogen. It's the simplest molecule that you can have. It's H2. There's two protons and two electrons that are joined together to form a molecule. Simplest molecule possible, and you look how vastly more complicated the spectrum is than the spectrum of atomic hydrogen. By the way, remember that these lines here are all produced by electronic transitions. So the visible lines are always produced by electronic transitions. So what we're seeing up there has nothing to do with the vibrational or the rotation aspect of it. Just the electronics, but the energy level structure is so much more complex in the molecule than it is in the atom that we get this much more complicated situation. And you can imagine, if you see that, I mean, to a certain extent, all molecular spectra are going to look alike. I hate to generalize, but you really have a thick distribution of lines like that. It's much harder to tell them apart than it is with the atomic spectra that are nice and simple like the one here. Okay, I guess I'll stop here for now, and we'll get up on Thursday and move on into chapter